Okay, then let's move on from in today's materials. Today, my goal is to finish the calculations with significant digits. If you will recall, on Friday, I left us hanging with one of our calculations in progress. That calculation had to do with addition and subtraction of scientific notation. Once I'm done with that, I will then move on to density, and we'll talk about density. And finally, we'll talk about energy, heat, and temperature. So, calculations with significant digits. Folks, multiplication and division is not so bad if that's the only thing you have to do, because the rule for multiplication and division is that the number of significant digits you record in your answer is equal to the measurement with the fewest significant digits. And in scientific notation, those significant digits are all found in the mantissa of the scientific notation, which is the first part of that number. So when you're doing multiplication and division, all you got to do is look at the mantissas and determine the number of significant digits from those. But where it gets complicated is when you're trying to do addition and subtraction. When we're doing addition and subtraction using scientific notation, the first thing you really should do is take that notation and get both numbers into the exact same format. So let's just look at this first part. We want to get 4.1 times 10 to the negative 3 and 6.9 times 10 to the negative 2 in the exact same format. To do so, the easiest way is going to be to convert one of these numbers so that the 10 to the minus number matches. And in this case, I'm going to do that with the first one. So it's going to be 0.41 times 10 to the minus 2 minus 6.9 times 10 to the minus 2. Basically, I took that 4.1 times 10 to the minus 3, and I made sure it matched up with the other exponent. At that point, we can perform the math. So we have we have 0.41 times 10 to the minus 2 minus 6.9 times 10 to the minus 2. And that comes out as a negative 6.49 times 10 to the minus 2. Now, if we're using our rules with addition and subtraction, we have to have the same number of decimal places. So that numerator simplifies to a negative 6.4 with that 9 as being the number that we would remove later on, times 10 to the minus 2. Again, we get rid of it later on. We don't do it now because we're not done with the math. We're going to do similar things to the denominator. So when we look at this, we have 8.943 times 10 to the 4th and to convert this times 10 to the 4th, we will make it I'm trying to do this real quick. So 5, 6, and we would be adding these times 10 to the 4th. Basically, I took the 7.2 times 10 to the minus 6, and I converted it to 10 to the 4th by moving the decimal back over. Looking at this, pretty much what's behind the decimal place doesn't matter in this particular case. So what really is going to matter is the 8.943, and we've got lots and lots of zeros, times 10 to the 4th. That's going to go into the denominator. Now that we have this in scientific notation and we're down to simply division, all that matters is our number of significant digits. We have 2 significant digits in the numerator, and we have 4 significant digits in the denominator. Therefore, our answer will wind up with 2 significant digits. So keying this into the calculator. You come out with a negative 7.257 times 10 to the minus 7. Again, now we're looking at what we need to get rid of. The digit we need to get rid of is a 5. And this is where that 5 rule comes in. Basically, we want the last digit kept to be even. Since the 2 is even, this would simply become a negative 7.2 times 10 to the minus 7.
Why do we want it to be even? Like, what's the logic behind it?
That's just simply the rule of 5s. Basically, when you have a 5 that you're going to drop, you look to the digit before it. If it's even, you leave it alone. If it's odd, you round up. That's just our rule of 5s.
So in this case, why didn't we round up?
What now?
Why didn't we round up on this one?
Again, the rule of 5. For a 5, so in answer to your question, the reason we just left it alone is because the digit we wanted to keep was even. In my opinion, the hardest type of problem to do is going to be scientific notation, multiple operation. That's the most difficult. And what makes it so difficult is the whole addition subtraction issue.
So do we do that rule for like all problems?
For any problem where the number you want to drop is a 5, yes.
Okay.
Okay, before I move on, I do want to make a note about calculations with significant digits. You will have 3 problems on this first exam that deals with significant digits. One will be making a measurement and recording it to the correct number of significant digits, like you did in lab last week. One will be just recognizing the number of significant digits in a value, similar to what you saw on the homework. And one will be calculation with significant digits. Other than those 3 problems, which you will also see on the final exam, that same type of problem on the final exam. Other than those 3 problems on the first exam and final exam, any other calculation in lecture on an exam, you don't have to worry about significant digits. Again, other than the 3 problems on the first exam and the 3 problems on the final, you will not have to worry about significant digits on any other problems in lecture. Now, because you have more time, I will expect you to focus on significant digits for the lab. You will always need to report things in correct significant digits in lab. But for lecture, it will only be the 3 problems on the first exam and the 3 problems on the last exam.
I have a question about the exponents on the equation. Like the exponents, do they have to be the same, like the lowest, like the lowest amount?
It really doesn't matter.
Just any.
They just have to match.
Okay.
Okay. So now what we're going to do is move on to what you will be doing in lab on Thursday, and that is density. Density is considered to be an intensive property. So before I get into density, let me describe the difference between intensive and extensive. An intensive property is independent of the amount of material. In other words, it doesn't matter how much you have. For instance, a little pebble of gold would have the same density as a block of gold. 1 milliliter of water will have the same density as 100 milliliters of water. It is an intensive property. Now, an extensive property is dependent upon the amount of material. An example would be mass. Obviously, that pebble of gold is going to have a much lower mass than the block of gold. An extensive property would be a volume. 1 milliliter of water is going to have a different volume than 100 milliliters of water. So intensive is independent, extensive is dependent on the amounts. Now, one of the reasons density is intensive, meaning it is independent of the amount of material, is because density is a derived unit where you take the mass and divide it by the volume. That is the formula for density. It is mass over volume. Now, with respect to density, what I will be discussing today, we will talk about how to calculate the density of an irregular object. We will talk about how to calculate the density of a liquid, and we'll talk about how to calculate the density of a regular object. We will also use density as a conversion factor. Now, I am going to do this in two different ways. I'm going to show you how to use density as conversion factor where I follow the units. And personally, this is my preferred method simply because I'm going to be using this method when I start getting into stoichiometry, when I start performing conversions with anything else. I'm always going to be following my units. But you can, with density, also use the density triangle. And I will, the density triangle has mass on the top and density and volume on the bottom. Basically, to go from top to bottom, you divide, and go from left to right, you multiply. So the mass is equal to the density times the volume. The density is mass over volume. The volume is mass over density. So basically that just helps you if you struggle with some of the manipulation of equations. So what I did is I did try to download a bunch of photographs so that you can hopefully not only do the math, but visualize what I'm talking about, since again, you will be doing this in lab this coming Thursday. So this first one is the density of an irregular object. One of the easiest ways to determine the density of an irregular object is through the displacement of liquid. So what the individual did here, see if I can't blow this up, is they masked the item. They then placed that item in a graduated cylinder that was at 600 milliliters. And the change in volume is that it went to 800 milliliters. So let's talk about what we know. We know that the mass of this object is 482.63 grams. We know that the initial volume is equal to 600 milliliters. And we know that the final volume is equal to 800 milliliters. Now, no two things can occupy the same space. So the volume of the rock is equal to the volume displaced. So our volume of our rock would equal the final volume of 800 milliliters minus the initial volume of 600 milliliters. Or in other words, we're talking about 200 milliliters. So using our equation, the density is equal to the 482.63 grams divided by 200 milliliters. Or our density comes out to be equal to 2.413 grams per milliliter, which is the same as, let's see, that would be recorded as 2.4 grams per milliliter if I am focusing on significant digits. The reason, by the way, that I have two significant digits is because I actually have the volume. And if I look at it, I can read the 100 and the 200. That means I know the hundreds place. So my uncertainty was in the tens place. And your significant digits always include what you know for certain plus one uncertain digit. So it had two significant digits for that 200. Okay, let's talk about the density of a regular object. When you're working with the density of a regular object, you obtain the mass the exact same way. You place it on a scale and get the reading. But when you're dealing with a regular object, the volume is determined using geometry. In the upcoming lab, you'll specifically be using the geometry of a cylinder, or the geometry for a cylinder, I should say. So again, the mass is determined the same, but it's the volume. The volume, you'll use geometry. So let's just pretend that the mass of our block that I just showed you was 3.635 grams. And our block had the measurement of 6 centimeters by 3 centimeters by 2 centimeters. Density is equal to mass divided by the volume. So we know our mass, that's easy. We just get the mass directly from the balance. But we need to determine the volume. Since this is a cube of sorts, then our volume is going to be the length times the width times the height. Or in other words, it's 6 centimeters times 3 centimeters times 2 centimeters, which is 36 centimeters. So we would take that 3.635 and divide it by 36 centimeters, and that would be centimeters cubed, because centimeter times centimeter times centimeter, that's a centimeter cubed. And our answer would come out to be 0.1 gram per centimeter cubed. Again, in lab, you'll be working with a cylinder. Now let's look at the density of a liquid. So they basically took 1.8 liters of a liquid, and it had a mass of, let's see if I can, 16.0 6.9 grams. It looks like. See if I can't blow this up. Oh, nope, 16.05 or 1605.9 grams. 16.05.9 grams. So we know our mass, that is the 1605.9 grams. And we know the volume because it's directly from our device, which was grams, was 1.800 liters. Now, what you do need to pay attention to is the units that it wanted it in, and it wanted it in milliliters. Well, 1.800 liters converted to milliliters, there's 1,000 milliliters in 1 liter. Whoops, wrong direction. I placed the liters in the denominator so that the unit would cancel, leaving me milliliters. And this comes out to be 1,800 milliliters. So I'll take that 1605.9 grams and divide it by 1,800 milliliters. And I get 0.8922 grams per milliliter. So in answer to this question, it would be F in this particular case. You will be determining the density of 2 liquids in LAM. And you will be using density as a conversion factor. So let's look at using density as a conversion factor. A chemist has a block of iron metal with a density of 7.87 grams per milliliter. The block weighs 1.90 grams. What is the volume of the iron block in milliliters? Again, I'm going to do this 2 different ways. The very first thing I do when I have a problem like this is I list out all the information I've been given. I was given the mass, which is 1.90 grams, and I was given the density, which is 7.87 grams per milliliter. Now, folks, when I see unit/unit, I change that. That is the same thing as 7.87 grams over 1 milliliter. The reason I do so is it makes it more obvious who the conversion factor is. Because when I work with a problem, and you'll hear me say this over and over, when I work with a problem, I always try to start with the value that has a single unit associated with it. So out of these 2 pieces of information, I want to start with the 1.90 grams. Now, I have grams in the numerator. I need to make sure I have grams in the denominator. So I'm going to flip my conversion factor and place the gram portion into the denominator and the milliliter portion in the numerator. When I do so, the grams will cancel and I will be left with milliliters. And I get an answer of 0.241 milliliters. Now, again, basically, by the way, this that you see is the same thing, just in case it's how you're more used to seeing things. As that. What it means is when I draw the vertical line, this means multiplication. And when I draw the horizontal line, this means division. So just for future reference, because I use this method of doing conversions all the time. Now, I mentioned the fact that we could use the density triangle. And basically, if we're wanting volume, then we want to take the density or the mass and divide it by the density. So we would take the 1.90 grams and divide it by the 7.87 grams per milliliter, and we would get the volume, which would come out to be the 0.241 milliliters. This will work. This second method will work for now, but in the future, it may not work as well. Any questions about that? I've tried to give you insight into most of what you'll be doing on Thursday regarding the lab. One more piece about density. Can anybody tell me why a ship floats on water? I will let you know that the metal of a ship is by far more dense than water.
Buoyancy.
But what causes the buoyancy?
The weight of the water or the density. The shape of it.
Not quite.
That's all I got.
It's okay. Anybody else? You mentioned the shape of it, the shape of a ship. Let's take a cruise liner. And we think about the shape of the ship. What is the primary thing within that ship?
Air.
Air. And air is less dense than water. So a ship floats because air is less dense than water. It's the same reason an ice cube floats on water. It's because it's less dense than water. So if we were to look at a diagram of multiple liquids, you would have the more dense object on the bottom. The medium density in the middle, and then finally the less dense object on top. So a ship floats because the majority of the ship is actually air, and air is less dense than water. So even though the ship is made out of metal, which is more dense than water, it's still going to float because of all the air. Okay, let's move out of density and get into heat, temperature, and energy for the last few minutes of today. We're going to start with energy. Energy, the equation for energy is that energy is equal to the heat plus the work, where heat is represented with a Q and work a W. In other words, heat is simply a form of energy. That's all it is. It's a form of energy. Now, if you're out at a campfire, you feel that radiating heat, because heat is always transferred from the hotter object which it's not letting me, there we go, to the colder object. So we typically feel that heat because we are cooler than the temperature given off by the fire. Now, with respect to molecules, as you add this heat, what it does is it causes the molecules to move faster. And as these molecules move faster, they can break the intermolecular forces that are keeping them together. In other words, they can actually tear apart these forces that have kept them together. So as you add heat, you are tearing apart those forces that keep these molecules together. And the molecules start moving faster. Now, heat and temperature are not the same thing. What we read as temperature is a result of this heat transfer. Basically, in the bulb of thermometer, you have molecules of a compound. And as heat is transferred to these molecules from the outside, these molecules move faster and faster. And as the molecules move faster and faster, they spread out. So really what the temperature is, it's telling us the degree to which these molecules are spreading out due to this change in the amount of heat that the molecules have. So heat is energy. Temperature is just a measure of how much energy is absorbed by the molecules in a thermometer, because heat is going to be transferred from the hotter object to the colder object. Now we have three different temperature scales that we can use. The one that is used by the folks in the United States for the weather is the Fahrenheit scale. The metric system scale is going to be, or I'm sorry, the most common scale we'll use in the laboratory is that of the Celsius scale, but it's going to be important that you can convert things to the Kelvin scale. Now, these equations that I have given you, the degree of Fahrenheit is 1.8 times the degree Celsius plus 32. This is the result of looking at the difference between the Fahrenheit thermometer and the degrees Celsius thermometer. And Kelvin being degrees Celsius plus 273.15 is the difference between looking at the Celsius scale and the Kelvin scale. Now, one thing you will note about temperature readings for both degrees Fahrenheit and degrees Celsius, you will see the degree sign. But you will notice that there is no degree sign used for Kelvin. That is because Kelvin is the absolute temperature scale. At 0 Kelvin, molecules stop moving. Now, on a test, I will give you these two equations. And you need to be prepared to use them. So let's look at an example in our last 5 minutes. The thermometer reads negative 111.1 degrees Fahrenheit. What is the temperature in degrees Celsius and in Kelvin? So I've got degrees Fahrenheit. The only equation that I gave you in degrees Fahrenheit was 1.8 times degrees Celsius plus 32 is equal to degrees Fahrenheit. So we know that our Fahrenheit is 111.1 degrees Fahrenheit. That's going to be equal to 1.8 times the degrees Celsius plus 32. Now, folks, the most common issue is doing the order of following the correct order in order to get degrees Celsius. The first thing you're going to do is subtract the 32. So negative 143.1 is equal to 1.8 times the degrees Celsius. And then you will divide both sides through by the 1.8 to get a degree Celsius of negative 79.5. Now we can convert the degrees Celsius into Kelvin using the fact that Kelvin is degrees Celsius plus 273.15. So our Kelvin is equal to a negative 79.5 plus 273.15. So it'd be 193.7. I actually finished a few minutes early today.